Hi everyone. So this is the live interactive session for week 2 of the course Introductory Field Structural Geology offered by NPTEL. My name is Rajiv Mukherjee and I'm a PMRF at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So we also conducted this live session the previous week where we discussed some multiple choice questions that were relevant for the introductory session of the course, and also some problems related to the structural attributes, especially linking the pitch, plunge, trend, deep strike, these kind of things with their trigonometry, and some stereonet problems, as well as some general general numerical problems based on large scale geology. So in this live session, that is 2nd August 2025, we will be talking about the lecture content of week 2. So in week 2 we learned about primary structures 1, primary structures 2, secondary structures 1 and 2, and basic lithostructural mapping. Again, I am inviting everyone to join these live sessions, whoever has enrolled for this course, that is the Introductory Field Structural Geology. We host these live sessions every Saturday for this 4-week 10 years of the course. The timing is 7 p.m. to 9 p.m. and this is the meeting link to join these live sessions. So before going on to the discussion session about today's topic, so what we learned in week 2 basically is the primary structures such as bedding planes, their compositional heterogeneity, distinguishing the bedding planes from the secondary foliation plane, differences between compositional grading and mechanically produced planes, penny-contemporaneous deformation structures, seismites, cross beddings, overturned cross beddings, and also determining the yonging direction from these penny-contemporaneous structures. And then comes the secondary structures such as mostly penetrative and non-penetrative, and from that we discussed about foliations and lineations, type of secondary planar fabrics, and how they interact based on the rheology or the strength of the material, that is also known as the cleavage refraction property, and its mechanisms. Then comes crenulation foliation, how fast generation foliation planes are being developed to second generation crenulation foliations, intersecting lineations, stripping lineations, mineral lineations, also the pressure saddle lineations. And from all of these data, from the planar data, that is the primary bedding plane, secondary foliations such as S1, S2, and so on, and also from the structural attributes of these different kinds of lineations, we learned how to determine the fold axis from regional structural data. And finally, using all these knowledges, we had a glimpse of basic lithostructural mapping, which is carried out in a regional scale. So culminating all of these new things that we learned in week 2, In today's discussion, we will be learning, we will be interacting about all of these kinds of problems. We will solve some MCQs such as we did before in the previous week. And if there are any doubts before going on to any some problems, I would like to ask whoever has joined this or watching this in YouTube to please leave comments if you are watching through YouTube about your doubts about these weekly sessions and also of the overall course. And whoever has joined today, if you have any doubt, you can ask me. And if not, then we will be going straight ahead to these conceptual problems that I have designed, some 12 to 13 problems that we'll be talking about today. So let's get started. Okay, so I think that in the previous week we ended our discussion session with some trigonometric problems related to the structural attributes. So today, first few questions or some more, we will be mostly dealing with stereo net problems. Now, stereo net problems are, I'm not going to use stereo nets actually per se. I will be drawing freehand, and from an overall guess, an educated guess will tell me what will be the correct answer from these four options. So that is how we will be solving some of the stereo net problems in today's discussion. And other than that, there are several problems or conceptual questions related to the folding. So we learned a little bit of folding mechanisms in week 2, not entirely folding, but the what we observe in the field, we did not observe any um, a visible fold in the outcrop scale, but we inferred from the mapping that yeah, there exists a fold in a regional scale, and there are some attributes of that fold that we measured in the field, and also some sin sedimentary deformation structures in different regions of Ghatshila. So altogether, we will be talking about these topics in different modes of conceptual questions. So the first question is, a coal bed is intersected by two mine drifts. In one drift, the plunge and trend of the apparent dip is 44 degrees towards 066. In the other drift, the apparent dip of the coal bed is 40 degrees towards 344. Use stereonet to determine the attitude, that is the strike and dip of the bed. Okay, so since the question asks to use the stereonet, so let us draw a stereonet. I will be drawing in freehand. I am not sure how good I can draw a circle, but I will try. It might turn out to be a flower dough, so pardon me for drawing such a mess. Anyway, I hope that we can say it is a circular stereonet with north, east, south and west marked. Now, first of all, we need to mark the apparent dip. Right, so apparent dip is similar to plunge and trend. For a line, plunge and trend is similar to the apparent dip of a plane and two planes intersecting, right? So the first one says that the dip is 44 degrees and it is towards 066. Now, as we know that when we measure the dip, we always rely on the great circles of these stereo nets, right? So this is my hemisphere or the equator, whatever you can say, of this stereo net, and these are 10-degree interval of great circle. So if this is 10-degree, I assume that this much amount of is 10 degrees. So then 20, 30, 40. So near about this much amount. So this will be the plunge amount, and there is a direction. So 066 means it is somewhere. So if this is 90 degrees, so 066 means it is somewhat lesser. Yeah, right. So this seems an accurate estimation of 066 on the stereo net, right? So if this is our 44-degree line, then we can mark this as P1, since this is the apparent dip of the first coal bed or coal drift that is being intersected by the coal bed, and we can mark the direction, right? So this is 44 degrees and the direction is towards 066, right? Similarly, 344 will be another another point, right? So I guess this is, you all know that this is 360 degree as well, not just 0 degree, but if you count uh, clockwise direction, then it will be 360 degrees. So for 344 it will be shifted towards the west somewhat around, I guess, this much. So this is 344, right? And it is pretty close to the previous point, right? So 44 degree and 40 degrees are almost close to each other. It's a 4-degree difference. So again, if I draw a 10-degree interval like this, a great circle, if it passes through like this, so I need to count 40 degrees from the west like this. So this is 10, 20, I guess 30, 40. So this is the so this will be the point now. And if I rotate that here, so it will come right like this, right? So this will be 0.2, and this is pointing towards, so this is 40 degrees and this is, I mean, the apparent deep direction is 344. So now what we need to do is to join these 2 points through a great circle, and easily we can say that the great circle should pass like this, right? This is how the great circle should look like. Now easily we can say that this is the deep, and this is the strike, and obviously it is dipping towards northeast, right? So this is 270 degrees. Now if we follow the right hand rule that we also learned in week 1, then we can say that if we place our thumb here, then all the fingers would point towards the dip direction. So if this is the strike, then we should count clockwise to get our dip direction. Similarly, in this case, this is the strike from which, this is the end of the strike line from which we should count the dip. Now we should focus on the options. So this is the strike end we are looking for, right? Not this one, right? Because if this is the strike end for which the dip direction has to be marked, and if we exactly follow the right hand rule, then you can guess that if this is the end of the strike line that we are considering, then obviously the plane has to dip in the opposite direction. But not that case, because we are getting the plane is obviously dipping towards northeast. So let us follow those options. The first option is easily denied because, yeah, the strike end is definitely not 060. Now what about 170 degrees? So 170 degrees is pretty close to the 180 degree south line, that is almost here. This is 170 degree. We are seeing no such strike end here, so definitely option B is incorrect. Now what about option C? Yeah, I guess this is pretty close because west is 270 degrees, and from that we are also going higher, and that means we are approaching towards 360, and somewhere between 270 and 360, the 300 degree mark should lie in this region. So this is a possibility. And another possibility, the 250, but the 250 strike end should be somewhere here because it is less 20 degree lesser from the west, so the 250 strike end would be here, and that would mean the plane has to dip entirely northwest, and the other end of the strike line should be along northeast. Then this option is also discarded. What remains is option C, and easily we can guess that the dip amount is also approximately equal to 50 degrees because obviously this is 40 and this is 44. So the great circle that is passing through this line has to have a dip amount greater than 44 degrees or at least 40 degrees. It cannot be less than 40 degrees, right? So if it is greater than 40 degree, then obviously, yeah, so 50 degree is the right choice, and most definitely 300 is the appropriate strike from which the plane has to be constructed, right? So option C is the correct answer. So we conducted, we solved the first question. Then let us move on to the second question then. So the second question says that a bed has a strike of 250 degrees and the dip of 40 degrees towards north. Plot pole to the plane using stereonet and choose the correct option. Again, I'm drawing a freehand stereonet. Yeah, this one's much better than the first one. Okay, so the information that we got is that it has a strike of 250 degree and dip of 40 degrees. We know this is 270, this is obviously 90, this is 180, and this is 0, or you can also say 360, right? So 250 means I have to go 20 degrees down this direction, and somewhere here obviously will be 250. This is a strike, and then the other end should be somewhere here, and since it is saying that it has a 40 degree dip, that means it is much steeper. So the great circle should be looking like this. So it is not exactly to north, but northwest kind of thing. So this is the bedding plane. Now pole means, so if this is a plane, it has 3 axes, right? So pole means perpendicular to this plane. Since in stereographic projection, planes get transform to lines, we reduce the dimensions. Then for lines, it would obviously become points. So like fold axis, pole is also an axis, and it will obviously come as a point. And that would be exactly like 90-degree opposite. I mean, it will be 90 degrees to the plane, right? So if I just count 90 degrees from here, so obviously this much amount is 50 degree. So then how much need I extra, how much do I need to go to 90? So we need 40, right? So in this case, we should assume that if this is our stereo net like this, we are going from here for 50 degree, we go around and then we come again 40 degrees from this direction to actually achieve 90 degree. That is how it is adjusted. Then exactly following the same strike and all these things. So from the opposite end of the strike, so if this is the plane, right? So if this is the plane, so this is the dip direction. So opposite end of this dip direction, we will just count 40 degrees, and this is somewhere the pole should lie. So which option will be the correct one? I'm sorry. So the deep is 40 degrees. I just I wrote it wrong. Sorry. I had to erase this one. So this is 40 degree. That means it has to be much steeper. So 90 minus 40, it is obviously 50. So the point will be at a higher position, like here. So this amount has to be 50 degrees, right? So obviously the deep, I mean this plunge of the pole will be 50 degrees. But then what will be the trend? So if you go like this, so obviously if we follow the right hand rule, so the deep direction would be towards north. That means um, 250 plus 90 would mean it is 340, right? So 340 will be the deep direction. Then what is exactly opposite to 340? So we need to minus or subtract 180 degrees. And that would get me 160 degrees, right? So 180 plus 160 is 340. So this direction is 160 degrees. So obviously the pole would plunge towards 160 degrees, and this will be the correct answer, option B. Okay, so the next question. In an outcrop, a symmetrical sin form is exposed. The attitude of the two limbs of the sin form is 340 degrees, 350 and 50 degrees. Sorry, 030 and 50 degrees. With the help of StereoNet, plot the attitude of the limbs and choose the correct option. Right? So the first point is 340 degrees. So this is the strike 300, and it will be like what? It will be dipping towards northeast, right? And it is 40 degrees. So this is the dip direction. This plane. This is plane 1. Okay. And another plane is 03050 degrees. So if this is north, then this is around 030, I guess. And from there we should count 90 degrees like this. So we should go clockwise. So this is how the other limb of the fold should look like. So this is limb 1, and this is limb 2. Right? So limb 2 has an attitude of 030. Oh, it is 50 degrees. I'm sorry. So I've drawn um, nearly about 30 degree. Okay, it's like this. Now this dip direction is towards 120 degree, right? This dip direction is obviously along 030, and this is around 120 degree. Then obviously we will get the intersection. So this intersection is obviously the fold axis, right? And it has a plunge amount. Where does it plunge? It plunges towards northeast. Then we can get the 4 options, right? So the first option says the axial plane is horizontal and fold is a non-plunging. Obviously it is wrong. Second option, axial plane is steep and the fold is non-plunging. We do not know whether the axial plane is steep or not, but for sure that the fold is plunging. So option B is wrong. Option C, the axial plane is horizontal and the fold is a plunging. Option D, the axial plane is steep and fold is plunging. Both options can be correct because we are not measuring how much the axial plane is dipping, but it is for sure the axial plane is not horizontal, right? Because axial plane, if the axial plane is horizontal, then it is very difficult to get a plunging fold. So it is definitely option D, because in this case whether we do not know the how much the axial plane is dipping, but for sure, yeah, so it is not horizontal and the fold is also plunging. So option D seems the right answer in this case. Okay, so we have solved 3 questions. Let us now move on to the next question. So question 4 says a horizontal bed is folded in a manner that the axial plane of the fold is vertical and strikes north south. If it is a non-plunging fold, the amount of dip of the bed in the hinge zone of the fold is, and there are four options given: 0 degree, 30 to 50 degree, 50 to 70 degrees, and 90 degrees. So this question is, I guess, easier for many of you who are seeing this right now. So I am pausing for a minute and I am letting you to think what will be the answer. Then I will resume again to discuss what exactly will be the solution. Okay, so let us draw a fold first. We are assuming this is the north direction, right? And we have been said that axial plane of the fold is vertical and strikes northwest, right? North south, sorry. So this has to be the axial plane like this, as it is vertical. Right? So this is our axial plane. Now, if this is the strike, and if this is the fold axis, so if I mark fold axis on this plane, provided that the fold is non-plunging, therefore the strike and the fold axis has to be parallel, right? So this is how the fold axis should look like. It is exactly parallel to the strike line. Okay. Now the thing is, how do we generate a fold axis? So the fold axis is generated from the intersection between a bedding plane, that is the limb, and the axial plane. So if this is the fold axis, then we can say that the fold is passing like this, right? So it has to be the fact that at hinge zone, If this is the bedding plane that has been folded, at the hinge zone, it has to be horizontal to intersect horizontally with a vertical plane, and that would give rise to a horizontal line. Right? So in this case, option A is the correct answer. That means the bedding plane at the hinge zone is horizontal. Okay, so let us proceed to the next question. In a syncline, all rock layers, option A, dip towards the fold axis, option B, dip away from the fold axis, option C, have vertical dips, option D, have horizontal dips. So this is, I guess, a normal question for a syncline or a synform. So again, I will pause for a minute and I will let you know, let you guess what would be the correct answer for this. If you have a correct answer, please feel free to say, and if not, then I will obviously solve this one. So if I have a syncline or synform, what would it look like? Like this, right? So this is the imaginary axial plane, these are the limbs of the fold, and it is constituted with the bedding plates, right? There are layers here. Okay, so the fact is that they all have to dip opposite to each other, but in a fashion that they always dip towards the fold axis. If it is dipping away from the fold axis, then it has to be an antiform. Geometrically, then for all synforms, they all dip towards the fold axis. That would be the right answer. Right? So if it was a antiform, then it surely would have dipped away from the fold axis. Okay, so moving on to the next question, question number 6. Which of the following features may not be used to distinguish between a primary foliation and secondary foliation? Option A, reversal of sequence in an exposure, existence of symmetry planes in the exposure, compositional similarities between layers, along stripe thickness variations in the layer. So these are some, there are some criterias. So we definitely discussed today about, I mean, not, we definitely discussed in this week two's lecture contents that how a secondary plane differs from a primary plane, right? So in case of primary planes, we mostly talk about um, bedding planes that are sedimentary or that are from the sedimentary origins. But there can also be igneous layering, right? Like Schlieren structures or layered magma deposit or lava deposits. So they can be called as trappeans, and there can be some kind of layering, but although those are not formed due to deformation processes and therefore they are of primary origin, right? But in most general use, the primary foliation that we talk about generally considers sedimentary origin of the beds, right? So then there can be several criteria, of which a few were also discussed in the week two's lecture content. But apart from that, there can be several other distinguishing features from using which we can differentiate between what are primary planes and obviously what are secondary planes, right? So the first option that we see here talks about reversal of sequence in an exposure. So if you think of an exposure, a very long exposure, you are seeing at a profile section, it has a very good road cut and some of the features are very well exposed, neat and clean structures. You go along the exposure and find that after a certain plane, reversal of sequence is reversal of sequence you start to get. Now, what do I mean about reversal of sequence? Reversal of sequence means the geometric dispositions become different, right? So, first of all, say for example, you are observing in the field that there are alternate uh, shale and sandstone layers in a region, but then you cross a particular area and then you find that uh, the sequence is not matching, or there can be a situation of overturning. That means a reversal of the younging direction uh, of the rocks. Whatever be the case, if it is occurring after a certain, I mean, after if it is occurring beyond a distinctively narrow zone, it definitely has to be a fault, because only a fault or a fault is kind of discontinuity that would disrupt this sequence. And also another possibility will be existence of an overturned fold, in which case you cross from one limb to another in an exposure and you would guess, I mean, you would see reverse sequence in terms of the younging direction. That is also a possibility. So in a general sense, reversal of sequence in an exposure definitely is a criteria using which you can delineate exactly from where the discontinuity between the structures starts to appear, and therefore there is an existence of primary plane and a secondary plane, and you can definitely figure out if this is, if a fault has happened, then obviously the fault plane is a secondary foliation plane, secondary structure, although it is not penetrative, but it obviously is a secondary structure happened due to deformation. Then you can mark that as a later stage phenomena other than the deposition of the initial sedimentary sequence. But then again, if you get reversal of the sequence in an exposure, it can also be due to ductile deformation. An overturned fold has formed, and you're going from one limb to another, and you are definitely getting a reversal of sequence. And following that, criteria, you can delineate between the overturned limb and the normal limb, and then you can eventually figure out what is the axial, what is the orientation of the axial planar cleavage in that region, and definitely you can distinguish between what is a primary foliation and what is a secondary foliation in that case. So option A is definitely usable, fruitful criteria, and that doesn't enlist as not a good criteria. So option A in this case is wrong. Now, existence of symmetry planes in the exposure, right? So you have seen the crenulations. Crenulations are pretty much small scale folds that are generating some symmetry, or a pressure shadow lineation existing on the secondary foliation planes. They definitely show a symmetrical pattern, right? Crenulation cleavages. So there is, so if the things are organic, as was shown in the lectures, it is definitely a true criteria that if things occur naturally with variation in their disposition, then definitely it has to be of primary origin. But if there exists a mechanical origin behind the generation or the production of these kind of secondary foliations, then it has to be symmetry. So secondary foliation, by virtue, if there isn't that much amount of heterogeneity in the rock composition or that much amount of anisotropy in the rock, it generally follows a pretty much symmetrical nature. That means across the plane you get symmetrical features, and one of the most prime example for this is the existence of the crenulation cleavage. Crenulation cleavages are the folding of the first generation secondary foliation plane. That means folding of S1, and that gives rise to the spaced cleavages. And if you just plot the attitude, if somehow you have a very tiny Brunton compass and you can measure the attitude of each of these limbs of the crenulation cleavage, and eventually if you plot them in a stereo net, you will see that the angles are equal, and the S2 S2 foliation plane is obviously a plane of symmetry, right? So for this purpose of question 6, B is also not the correct answer. Compositional similarities between layer, obviously compositional similarity, that means if you follow along and if you see that a homogeneous composition is present and then it is being alternated for a couple of mm, I mean in a couple of dimensions, horizontally, vertically, whatever, it has a thickness or it has a length or width, whatever, and it is being repetitive, right? So this compositional contrast is definitely a criteria that can delineate between primary foliations and secondary foliations. So option C is also not correct in this case. So what remains is option D, and as you can see, option D is definitely a viable criteria, because along strike thickness do vary in case of primary layers, primary foliations, right? So if you observe the bedding planes in Ghatshila, you will see that there are several variations in thickness. Even if you follow the strike line of the bedding planes, the H0 planes, and these variations are natural because they follow different sedimentation rate at different time period, and obviously there can be a variation not only along the strike. So if you have a section, you're traversing through the section, you can see that there can be uh, I mean pinching out of the sedimentary beds, right? And there can be disruption in sedimentation process that can also give rise to uh, varying thickness of a same bed in different exposures. And also it is true for secondary foliation planes as well, because if you go along, if you follow a heterogeneity, along strike heterogeneity in composition, the foliation plane developing within that heterogeneity will also reflect its spacing, right? So if you have a very coarse grained material for some region, then you will get spaced cleavage. And then if you just follow the same deformation, same phase of deformation into another lithology, you will see continuous cleavage, because it might be of fine grain size or weaker material. So the spacing between or the thickness variation between a same phase of deformation or the secondary foliation, or the same the thickness variation for a same bed in case of a primary foliation, doesn't seem to be a good criteria to delineate between what is a primary plane and what is a secondary plane or secondary foliation. So in this case, option D is the correct answer, right? Okay, so let us move on to the next question. Question 7. Which one of the following interfaces is likely to be considered as a secondary foliation? Option A, the interface between an underlying granitic gneiss and the sandstone unit above it. The interface between a shale sandstone layered sequence and the dike cutting across the unit. Option C, the interface between a formation where grain size starts to change. Option D, the interface between the host rock and quartz vein intruding along a fault plane. Now, these kind of questions um, are actually pretty good, so it can nurture what you think about secondary foliation and primary foliation. So I will pause for another minute and let you guess what would be the answer, and then we can talk. Yeah. So the first one, option A, tells that the interface between an underlying granitic gneiss and the sandstone unit above it might indicate that it is an interface of secondary foliation. Well, if there is a certain disposition between a sandstone and a granitic gneiss, we all pretty much know that this has to be an unconformity. Right? So this has to be an unconformity, because there has to be a separate time period between the metamorphism of a granite gneiss and the deposition of a sandstone, right? So it is most likely that the granite gneiss is a supracrustal rock above which, or the basement rock above which, the sandstone unit or the alluvium is deposited. So that has to be a drastic change between the environment of deposition and deformation. So option A is not a correct answer, because it is not a secondary plane, it is just an unconformity. So unconformity means a general hiatus or a gap in time where there are no records of the, I mean, there are no records of the geological history. The archive is missing from that period, and it is likely that an unconformity can even indicate even a billion year of age difference. That is also possible. So unconformity is not a secondary plane; it is just a gap in time, right? So then comes the option B, which says that the interface between a shale sandstone layered sequence and the dike cutting across the unit. So the thing is, a dike that is cutting across a shale sandstone layer, there has to be, again, there has to be difference in time period, right? So shale sandstone is cut across um, by a dike. Now the thing is, although it is a form of brittle deformation, tensile fractures has happened, and uh, the dike material, it got intruded, and it cut across the interface of the alternate shale sandstone sequence, but it still carries a signature of brittle deformation. Now one another thing is interesting, that apparently there is no chance for developing a foliation in the mm, shale sandstone alternate layers. The thing is that if there is little to no differential stress acting perpendicular to these layers, or whatever, oblique to this layer, so that there can be some signatures of ductile deformation, the secondary foliations that we observe in this case might not be present, right? But at the interface, due to the intrusion of the dike and due to possible rise in temperature, probably near about 700 to 800 to even 1000 degrees centigrade, a dike can actually cause high temperature plastic deformation of the materials, especially the sandstone shale alternate sequence. There can be some sort of contact metasomatism or contact metamorphism in this case, because both the sandstone and shale, they contain some sort of water or fluid in them, as they are sedimentary deposited materials. And then because of that high temperature, there can be dehydration reactions. In particularly for shale, it is well composed of clay materials. They react to each other, and there are also quartzofeldhatic and some mafic elements. And because of the existing reaction due to high temperature, because of the dike intrusion, there can be some secondary mineral formation like hornfels structures, and there can be a development of a baked zone, but that thing is exactly not what we can expect um, from a die cutting across the unit. So that the interface can be, I mean, the interface can carry some signatures of ductile deformation that can be counted as a secondary foliation plane, but it would definitely not go beyond the interface to some extent regionally over the shale sandstone layers. It will be restricted only near to the dike intrusion, and there is a possibility it can carry some secondary foliation planes, but those are, I mean, not um, those cannot be penetrative structures, right? Now the interface between a formation where grain sizes starts to change. So in a formation, if you see grain size is varying, that means we are talking about a sedimentary formation along which, in a sedimentary sequence, we find an interface. We assume that the sedimentary beds are all horizontally deposited sedimentary beds lying top of each other, and we find the interface below, from which the grain size starts to change. Now, if we find that in field, we would generally term that thing as a facies. Right? That is a completely different lithofacies, because change in grain size, whether it is finer or whether it is coarser, whatever may be the case, change in grain size generally represents change in the depositional energy. So for high energy conditions, we will get coarser grain size. For low energy depositional condition, we will get finer grain size, right? So that is how you also get those peri-contemporaneous structures, because of the very fine grain material. For coarse grain material, water can escape easily because of high permeability and porosity. But for small grain size material, even though the porosity is high, we get little to no permeability, and the water only can escape from the layers if the sedimentation process is disrupted by rapid and conspicuous tremor or shake, and that is how water escape would leave such remarkable structures that we observe in the field. So in this case, obviously, change in grain size, particularly for a formation, is not a function of the deformation. Now if we observe that change in grain size in a metamorphic rock with some deformation structures already present, then that could indicate that beyond that interface, there is some sort of recrystallization or grain size sensitive processes or plastic deformation that has contributed to smaller grain size material or larger grain size material. That can also indicate changes in the differential stress. It can also indicate changes in the pore fluid pressure. It can also indicate changes in temperature as well. So these kind of things then would definitely indicate a change in deformation condition, not the deformation itself, right? So option C is also not valid in this case, because generally for a sedimentary sequence, change in grain size would indicate a new facies. Now for the last option, the interface between the host rock and a quartz vein intruding along a fault plane. Fault plane is already a discontinuity, and it has been developed due to changes in the compression or tension like it can be a normal fault or it can be a thrust fault, whatever may be the case, it is also a signature of brittle deformation. But then again, if quartz vein has intruded simultaneously during the process of faulting, the host rock would experience high temperature and it would show signatures of annealing and also some deformation. And since faulting already um, involves a tectonic process, therefore intrusion of quartz veins along the fault in a host rock would definitely indicate that some deformation is being localized where where the quartz veins are intruding. And then again, it can also leave some signatures of temperature driven plasticity or ductility within the material, and it can also develop some local scale foliations within the material if the rest of the material is considered to be undeformed, right? Because um, fault is generally a brittle deformation signature, and we consider that it only occurs between rigid bodies, and therefore the rest of the material can be considered as undeformed, right? So for a undeformed host rock, even intrusion of quartz veins along a fault plane could give rise to local scale appearance of secondary foliations due to temperature driven plastic or ductility within the rock. So in a similar sense as of option B, option D can also be a correct answer. So in this case, question 7 does not appear to have a very clear cut answer, but rather we get a sense which are much closer to the question that has been asked, that is what can be considered as a foliation, secondary foliation apart from the primary bedding plates. Okay, so let us move on to the next question. Cleavages observed to be entering from a low competent layer to a high competent layer during folding. Which of the following options regarding cleavage refraction is likely to occur in this situation? Option A, cleavages will converge towards the trace of the axial plane in the incompetent layer. Cleavages will diverge away from the trace of the axial plane in the competent layer. Cleavages will diverge away from the trace of the axial plane in the incompetent layer, and cleavages will converge towards the trace of the axial plane in the competent layer. So cleavage refraction has been introduced thoroughly in the week 2's lecture content, and we have seen how the seen behind the uh, mechanisms of cleavage refraction formation. So apart from from these four options, you have to select the correct one, and it is a fascinating thing to talk about cleavage refraction. So I would spend another minute for you to think, and then I will um answer the question. So cleavage refraction is similar to what we see in optical refraction. So in optical refraction, if this is optically dense medium, and this is optically rarer medium, then the incident light beam has an incident angle and it has another angle of refraction, right? So if the light ray enters from optically rarer medium to an optically denser medium, then the light beam should converge towards the perpendicular, and then again exiting from the denser material medium to another rarer medium, it would diverge away from the perpendicular line, right? So in a similar fashion, cleavage refraction works as the same. So in case of optical optical density variation, like the changes in the refractive index, in terms of optics, we get competent and incompetent layer. That means there is a rheological contrast between the material. So if this is weaker material and this is stronger material, then it is incompetent, and this is the competent layer. Right? So if a cleavage plane or cleavage trace of cleavage plane is entering, right, from an incompetent layer to a competent layer, it would converge towards the perpendicular, and then again exiting from the competent layer to another incompetent layer. So if this is incompetent or weaker, it would diverge away from the perpendicular direction, a perpendicular line. So this follows. Option A tells cleavages will converge towards the trace of the axial plane in the incompetent layer. Obviously, no, it will diverge away. So option A is not correct. So this is the trace of the axial plane, right? Option B, cleavages will diverge away from the trace of axial plane in case of competent layer. This is also not correct. Option C, cleavages will diverge away from the trace of axial plane in incompetent layer. Yes, this is correct, as we can see that it is diverging away. Option D, cleavages will converge towards the trace of the axial plane in competent layer. Yeah, it is also correct. So option C and D, these are correct answers. Now going to question 9. Rock A and rock B both shows compositional bending and no macroscopic signatures of deformation on a hand specimen scale. How would you determine the existence of a secondary foliation from these rocks? Option A, only by studying the mineral assemblage. Option B, only by studying the shape of the mineral grains in thin section. Option C, by studying the mineral assemblage and observing the microstructures in thin section. Option D, only by observing the microstructures in the thin section. So in hand specimen scale, it is obviously not possible to find any kind of microscopic signatures of deformation, right? And then only by studying the mineral assemblage, it is very hard to tell whether the rocks are deformed, or rather we cannot determine the orientation of the secondary foliation planes just by observing the compositional banding. I guess, I mean, if I give you a sandstone, or say for example a shale and a granitic gneiss, okay. So how could you actually differentiate between the two in terms that which one is deformed and which one is undeformed, right? So it is very hard to tell only by the hand specimen observation. We need secondary information for these kind of assessment. So only by studying the mineral assemblage is not the correct answer. And also by studying the shape of the mineral grains in thin section, it is very difficult, because in which direction you are cutting the rock to obtain the thin section would determine what will be the shape of the mineral grain that you are observing in microscope, right? Say for example, if I have, I mean, a fibrous material, right? Some asbestos material. So these fibrous grains would have some linear alignment. Then if I cut a section parallel to this alignment, I would obviously see lines, traces of lines of those minerals, and they're pretty much oriented in the same direction. And the shape would be very much anisotropic with a high eccentricity. If I fit an ellipse to estimate the aspect ratio of the grain size, I would get a very high eccentricity or a very high aspect ratio. Would that mean that the rock, the material is deformed? No, because if I cut a perpendicular section to that, I will see circular sections of the asbestos, and then it would be hard for me to tell whether the material is deformed or not, right? So in following lectures, you would also learn about kinematic reference frames, XYZ coordinates along which the rock should be cut to get a proper thin section and to study the signatures of deformation. But for now, let us just focus on the fact that just observing the shape of the mineral grains is not a good idea, because it can be heavily biased on the orientation of the thin section as well. So option B is not also a viable choice to determine whether to determine which is the secondary plane in this case, right? Now the option C is by studying the mineral assemblage and observing the microstructures in thin section. That is the only true answer to this question, because you need to look at the microstructures. Now microstructures, generally the term microstructures indicate how different mineral grains are existing with each other, and due to their coexistence, how they are accommodating the space, right? So that is in general term microstructure. That means we are trying to recognize a pattern in micron to submicron scale. We observe the grain boundaries, we observe the grain size, we observe the grain shape, we observe the interlocking pattern, we observe the bulging and migration of grain boundaries, right? We observe the structures within the grains, if there are some formation of subgrains, some high angle grain boundary, low angle grain boundary, decrystallized grains. about to recrystallize grains, relic grains, porphyroclast, porphyroblast, tail of a porphyroclast, pressure shadow zone. All these kind of things are generally coined as the term as, microstructure, right? So microstructure is a very important aspect for studying the deformation in structural geology, right? And different kinds of material will also show different kinds of microstructures, and they are mostly delineated from each other through their optical properties, right? So the most common signature of deformation is captured through undulous extinction in quartz. So if you observe a quartz grain in thin section through the polarizing microscope, and if you see that the extinction angle is varying within the single quartz grain, that means there is a undulation in the extinction angle, and then you can see different shades of gray passing by the quartz grain as you are rotating the stage. That means it is, the extinction angle is changing systematically within the grain itself. It is a signature that the crystal lattice itself has been bent, and that is how we can say that, okay, so there is a subgrain formation within the uh, mineral grain, and this indicates that it has just been arrested while dynamic recrystallization process was going on. So this has been the relic grain, and there are still some signatures of deformation arrested within it. That indicates the rock is deformed. You generally do not get these kind of features in a sedimentary terrain, a sedimentary rock, because there are some other microstructures that you observe in sedimentary rocks, like the cement material and the matrix material, the grain size and the size of the clasts, and what are the compositional heterogeneity that we observe. Very often we find, it is also normal to get deformed quartz grains or other feldspar grains inside a sandstone when we are observing through thin section. But the thing is that in that case, you won't find any particular orientation. There is no systematic repetition of the microstructure that would allow us to determine what is the orientation of the secondary foliation plate. That is how we can delineate between undeformed rock and a deformed rock. So probably what had happened is that the quartz grain has come from erosion of an exhumed deformed rock, and that particular grain is now being deposited in somewhere else. So there is a terrestrial deposition, right? And from that the sandstone has formed, but then it has entrapped these deformed quartz grain. But that doesn't mean the sandstone is deformed like that. But in case of a granite gneiss, if you have secondary foliation planes, of contrasting bands between so melanosome, ligosome, these kind of bandings, if you're observing in a granitic gneiss, and if you just cut the rock and observe in thin section, you will see a good development of shape preferred orientations or crystallographic preferred orientations within the rock microstructure, and the microstructure itself will tell you whether the material is deformed and not. And also important thing is the mineral assemblage, right? So what kind of minerals are you assessing to be present in that rock? That would also tell us about the pressure temperature condition at which the rock has undergone this deformation or metamorphism, and whether at all these are the signatures of deformation or not. These are also very much crucial information that we get apart from the deformation structures, deformation microstructures, and from the mineral assemblages, right? So for example, if you get kyanite or glauconite, right, in your glaucophane in your rock, yeah, so that would definitely mean that it is a very high pressure temperature rock. It would definitely show some signatures of deformation, like the development of a shape preferred orientation or something like that. Apart from that, you can also even say that, okay, so kyanite is present, and okay, so glaucophane is present. That means the assemblage has suffered high or experienced a very high pressure and temperature of deformation. So it definitely is a metamorphic rock, and therefore it has to be some deformation in it, right? So option C is the viable option, because just by observing the microstructure, you cannot identify how much metamorphism has taken place within the rock, and you need to also understand what kind of mineral assemblies is actually showing these microstructures that can confirm the existence of a secondary foliation plate, right? So option D is not too that much viable like option C. Okay, this one is very easier question. So if the slope angle of the ground surface is more than the depth of a bedded sequence, and if both the ground and the beds are inclined in the same direction, then option A, younger beds will be made within the direction of the dip. Option B, older beds will be made within the direction of the dip. Option C, younger beds will be made at the opposite direction of the dip. And option D, only the oldest bed will be made with as one goes in the direction of the slope. So if I have, say for example, I have multiple bedding planes, right, and this is the younging direction. So this is the youngest bed, and this is the oldest bed. Right? Now the question asks that the slope angle of the ground surface is more than the dip of the bedded sequence. So if I cut across like this, and if I say that, so this is the ground surface slope, it is pretty steep, then what is the dip of the sedimentary beds that have been sequenced, right? So this is the slope direction, obviously, right? So this is the slope direction. So if you just go along the slope direction, you will get what? Older and older beds, right? So option D is only the correct answer, because you will get only the oldest bed will be made with as one goes in the direction of the slope, right? So if you go along the slope, you will get older and older beds. Okay, so since we had lithostructural mapping in week 2, so I thought to put a question about plain paper maps. So the question asks, identify the folded structure. If the fault plane dips 70 degrees down to south, then determine the nature of the fold. Determine the nature of the fault, not the fold actually. And what is the timing of the dike intrusion? Right? So, and in the map, you are seeing that the following geological map shows exposures of sedimentary beds PQRST, right? And a batholith that is hatched in a flat terrain. So then there is a dike XY FF fault, and U is the unconformity, right? U is the unconformity. Okay, so first of all, let us see that in a flat terrain, when you are getting a fold, trace of a fold, in a flat terrain, that definitely would mean the fold is plunging, right? Right. So if I consider this is R, this is Q, and this is P, the entire fold is plunging like this, and in the cross section I get the folded shape, right? So obviously P has to be the oldest bed, and R is the not oldest, yeah. P is the oldest and R is younger. So by the I mean type of fold, if I have to understand what is the type of the fold is plunging, and it is definitely an antiform, and most likely an anticline. Right. So in a sense that P is older than Q and it is older than R, and then again we see that it has been there are other depositions in this direction. It comes as so the bit S and T, they come after R in this direction. So R is the final lithology, and after that there are S and T. So just following the uniformitarian rule, we can say that even S is younger than R, and eventually T is also younger than S, right? So this can be a sequence that we can uh, infer. Okay. Now there is a fault if dash, right? Because of the fault if dash, this part has become enlarged. So if this was the first trace of the fold, now it has become much bigger, which means this part has moved up upward like this. This part has moved upward, and this contains the trace of the fold, and this one was relatively towards the down, right? The hanging wall, sorry, the foot wall, and this has the hinge part, and the limb, traces of the limb remain in the hanging wall, and it was just thrown upwards, and that is why after erosion we get enlarged form of uh, the trace of the fold. So there is a discontinuity, and obviously since it is dipping south, if this is north and this is the south, so the fault is dipping towards the south, and then we can comment that the fault is a southerly dipping thrust fault or reverse fault. It is definitely reverse fault because the angle is 70 degrees. So we know that if a fault is if a fault is uh, less than 30 to 45 degrees dipping in that manner, and it is uh, a thrust fault, like this reverse motion, because fault formed because of compression. So it is thrust fault. And if a fault that has also formed because of compression but now has an angle of deep angle of 70 degrees or so, that means it is beyond 60 degree, it is termed as a reverse fault, right? So the fault is southerly dipping reverse fault. Okay. And obviously we can say that the sequence of events took place like, first was the deposition of P, then deposition of Q, and then deposition of R, then folding of PQR as in the form of an antiform, plunging antiform, right? Then the deposition of S, and then the deposition of T. There is an angular unconformity between R and T, obviously, R and S, because initially it was folded, now it is some horizontal beds with a gentle dip towards the north. So there can be a possibility that this boundary UU is an unconformity, which is an angular unconformity, right? So UU dash is an angular unconformity. And altogether this sedimentary sequence, deformed sedimentary sequence, after the folding, then comes the angular unconformity, and then there is a deposition of S and T. And um, the faulting definitely took place before the deposition of S and T, I guess so. That is hard to tell the timing of the fault just from this information, but most definitely that the batholith has intruded after the deposition of S and T, as it has been cross cut by this large batholith, and then the dike cross cuts all of the existing features in this map, because since the batholith is overlying S and T, then it is definitely younger than S and T and R, all this lithology. And then the dike itself cross cuts the batholith. So this can confirm that the dike is the youngest intrusion. Okay, so now let us move on to the next question. So the next question is not exactly an MCQ, but I would rather like to give an information about classification of different types of foliation planes, because mostly on the secondary foliation planes, because in this week we learned about um, a lot about primary and secondary foliations. So I think it is better to get a classification scheme for secondary foliation. So uh, morphological classification of secondary foliations. So the secondary foliation starts with spaced and continuous. That has already been discussed in details in the week 2's, lecture content. Okay. Now, there can be three primary classifications of the spaced cleavages. One is compositional, spaced cleavage. Another one is disjunctive, spaced cleavage. And the last one is crenulation cleavage. So compositional spaced cleavage can then be subdivided into again two categories. One is banded and the other one is diffused. Disjunctive spaced cleavage can be categorized into four classes. The first one is stylolytic. Second one is anastomosing. The third one is rough disjunctive. And the last one is smooth disjunctive. So these are based on the cleavage, microlithon shape and spacing. Based on the relationship between the cleavage and microlithon, their shape and the mutual spacing, we classify the disjunctive cleavages according to four classes. Then comes crenulation. Crenulation can be divided into two categories. One is zonal crenulation and the other one is discrete crenulation. Right? And then comes the continuous cleavage. Again, continuous cleavage can be classified into two categories. One is fine continuous and the other one is coarse continuous. So the fine continuous cleavages, they can also be classified into three categories. One is microcrenulation. One is microdisjunctive. And another one is microcontinuous. There are no reported morphological classification for the coarse continuous cleavages, because it is a very rare to get coarse yet continuous cleavages. So now the last question is that discussion about how pressure shuttle lineations form. So pressure shadow, you know one thing is that pressure shadow forms based on the high competency contrast. Between the matrix and the porphyroclast or porphyroblast, right? So this is a rigid, body which suffers little or no deformation, so it accommodates all the stresses, right? And it creates a strain field like this, diverging away from the point of high stress. And because of that, since the stresses are diverging in this direction, it creates a lack of pressure just following the equator of the or the middle hemisphere of this rigid clast. And that's where fluid related depositions and precipitations take place, and that is how we get pressure shadow lineation. But the thing is that it requires the presence of a porphyroblast or a porphyroclast, right? And there are dominantly four categories of porphyroblast. So the first one is the pre-tectonic. P means the the age of the porphyroblast, and D means the deformation phase. So if the porphyroblast exists even before the deformation, then the new phase of deformation just warps around the pre-existing porphyroblast, and that is how we can define the pre-tectonic porphyroblasts. Intertectonic porphyroblast means some kind of mineral growth has taken place intermediate in between two active deformation periods, and it generally cross cuts the previous foliation, but then again gets deformed at the second stage of deformation, right? Syntectonic porphyroblast means that the porphyroblast the growth of the mineral takes place simultaneously along with the deformation event. That is why P, the formation of the porphyroblast, is a subset of the existing phase of deformation. And in general, in this case, the foliations, the internal foliations within the porphyroblast matches well with the external foliation. And last category is the post-tectonic porphyroblast, which simply overprints the pre-existing deformation event, and that is how we get porphyroblast which does cross-cut the pre-existing foliations at the signatures of deformation, and they do not show any sense of rotation or pressure shadow formations. So post-tectonic, in case of post-tectonic uh, porphyroblast, we would not expect any strain shadows or pressure shadows, that therefore there can be no formation of the pressure shadow lineations. But in case of pre-tectonic, intertectonic and syntectonic porphyroblast, there can be existence of pressure shadow or the strain shadow that can lead to pressure shadow lineation formations. Okay, so this was all for week two's discussion, and I hope everyone got to understand what we discussed today. So if anyone has any doubt related to today's discussion, they can leave comments on the YouTube where this video will be uploaded. And as usual, uh, the, the, the the drive link, Google Drive link, where I will be uploading the link for the YouTube video, and also the lecture notes will be has already been shared with you. So in the first week, I have also uploaded all the lecture materials along with the YouTube video. I mean the recorded video that has been uploaded to YouTube. You can go check out to that, and I will definitely upload to today's recording and the lecture material. You can also access them from the Google Drive link. So thank you for spending your time watching this video and the recording and the live session whoever joined, and we will meet again on the next Saturday, and we will discuss about week three's lecture content. So till then, good night and have a nice day. Bye.